Welcome back. There are theories which are been given or that probably the faults or the lineaments in the basement close to the front are responsible for the formation of this fan shaped landforms. And if you see back into the history of this, what is that has been noticed that the river has migrated and reoccupied its own channel in last 50 or 60 years. So, like in 1950 flowed at the same one as it is flowing now. In 1923 to 48 it flowed through this one, and further if I take here, if I am not wrong, here it is 1731 or 37 it flowed through this path, and in 1770 it was flowing through this. So, likewise it has been swinging all across this area and it has reoccupied its own channels at number of points. We have to be extremely careful in putting the settlements along these channels, and we need to have the understanding that why and when this shifting will take place. It is bit difficult to predict, but of course, as we have talked in the beginning, that sediment load, increase in sediment load and any influence by the human activity or climate change or tectonic activity can result into the change in the river course. But in this case, of course, we have the course is having the availability of its own channels, which it keeps on reoccupying again and again. Now, if we talk about the upstream and downstream floods particularly, what we will be able to see here is that the upstream floods, floods that affects the smaller areas, it is localized and caused mainly by the local cloudburst or the rainstorm or dam failure in the upstream region, and it will last for shorter period, whereas the downstream floods in the low lying areas will affect a very large region in the downstream side, and it will be mainly due to the prolonged heavy rainfall, last for larger period. So, time span between the upstream and the downstream floods will be quite different. The another part you can even talk about that, because in the upstream the gradient is quite steep, so it will allow the water to flow through very fast. So, runoff will be faster, but in the low lying areas, in the downstream side you will not have that facility available, because you are having very low gradient, and more area will be covered. So, this is the main difference between, if you have to classify the upstream floods and the downstream floods. Now, this is another important parameters which we usually consider. We are not going to discuss all, but few of them which are important we are going to talk in this one. That is the drainage basin evolution, then morphometry and drainage pattern. Quickly look at the fluvial geomorphology. It is a linear aspect of channel systems, aerial aspects of drainage basins, then we have channel geometry, and then we have processes which in different domains, then integrating the hydrology and geology. So, how this all affects the flooding conditions, and how it can be helpful in understanding the flooding conditions. Now, linear aspects if we take of the channel system, then we consider this as an surface area or the basin area, then we talk about the drainage pattern, then we talk about the stream order, that is the quantification of stream network, bifurcation ratio. This is extremely important, because when we are talking about that what will be the what shape of the hydrograph we will be expecting in different basinal areas, okay, that can help us in this. And then drainage density, okay, and drainage density will be affected based on the geology of the area. Now, this is one of the very general classifications which have been given, okay, that if you are having you have to order the stream, okay, and try to find out the bifurcation ratios of that, because this again depends on the drainage density, okay, and what is the order of your stream, main stream, or you have order of the tributaries. You can do the classification very easily. Now, the softwares are available which can quickly give you, if you are using the digital elevation models, okay. So, the ordering of the stream can be done in few seconds, okay. So, you are having like two lower order streams are meeting at one point. The further downstream will become the second order, and then if two second order streams meet at a point, the downstream stream will become the third order, and similarly two third order stream meets here, then the main trunk stream will be numbered as your fourth order stream, okay. Now, drainage basin, particularly we have in the beginning also we have talked about that this is what. So, if you take this the close up of this, and before going to that, if you look at that, this is the trunk stream of here, and this is another trunk stream, and there are some sort of an higher elevated region, okay, which allows the stream to flow in this direction and the other side on this direction. So, this is what we can say the ridge line, okay, that will make the basin boundary, and this whole area will be considered at the basin of this particular trunk stream, okay. So, we have the main or we can say the major basin area, and then which will also have the minor basin areas, okay, likewise which has been shown here, okay. So, you have the smaller basins here of this tributaries, and then you are having the major basin of this trunk stream, that is the fourth order, okay. So, this again shows the similar one. So, you are having the main stream and you are having some sub basins, okay, and this whole area will be marked as a major basin of that particular trunk stream. Again, an example of the drainage divide you are having. So, this is the portion which will mark the drainage divides and which allows or force the water to flow on either directions, okay. Now, usually what has been seen that once the basin, if you are having slope, you are having the precipitation, and if you keep the precipitation constant, there is an experiment which was conducted which shows that how the drainage basin grows, okay. So, drainage basin will grow towards the headward side, okay, and this is what we see, that you are having this is the fixed point here, but the drainage basin has eventually formed on the upstream side, that is what we call the headward areas, okay. So, channel network forms by bifurcation of headward eroding channels, okay. Now, coming to the drainage pattern, there are few which are important. One is dendritic pattern, which develops above the homogeneous geology. So, you can identify, you can know the subsurface geology also based on the drainage pattern. Then another is trellis pattern, which develops over the tilted or folded strata. Then you are having radial pattern, which develops over the domes or volcanic cones, okay. Let us see quickly what are these different patterns, okay. It looks like something like the irregular branches of trees, okay. It will be in different directions. It is commonly seen in massive rocks and the flat lying stratas, okay, due to strong resistance of rock. Headward development of the valley is negligible, okay. Whereas the parallel drainage usually is seen along the sloping surfaces commonly in the terrain with homogeneous rocks, development of parallel rills or gullies or narrow channels are commonly seen on gentle sloping surface also. Then we have radial patterns, which shows that the center point is comparatively higher and all streams are flowing away from this. Okay. So, this is typical of the high topography in the center. Okay. And then rectangular drainages are marked by right angle bends. So, you will see the right angle bends here. So, smaller streams coming and taking bend almost at right angle, commonly due to the presence of jointed rocks, fractures in the massive rocks or in metamorphic rocks which are having some foliations. Okay. Now, this patterns which we are trying to understand can also helps us in understanding that what will be the pattern of runoff in that particular region. Okay. If you are having massive rocks subsurface, then you will have very quick runoff. Okay. So, high runoff will be there, and suppose you are having rectangular drainages, it is possibilities are high because the area is having fractures or joints, then the percolation will be comparatively faster. Okay. Now, coming to the trellised one, these are seen in the areas where we are having the folded sedimentary rocks. Okay. And another one is annular one. The stream follows almost circular concentric path and mostly seen in the areas where we are having domes or basins. Okay. So, you can also understand that what will be the flow trend in these regions based on that, and also try to know, and we can know the subsurface geology. Okay. So, these are the examples of the dendritic pattern, how it looks like. Okay. If you are having radial, how it looks like, and if you are having trellised in the folded sedimentary terrains where you are having weaker and like stronger rocks, okay, then you will have this type of drainage system. And then if you are having the fractured ones, then you are having the rectangular drainage. Now, quantifying stream networks, stream orders, streams in a basin can be ranked using one of the several schemes. Okay. Now, flood intensity, if you take, okay, the flood intensity is considered to be a discharge along a channel over time. Okay. Flood intensity will be influenced by the rate of runoff, channel pattern shape, the number of tributaries and distance downstream. In stream order, the smallest tributary are designated as first order. Those were first order tributaries join together will be the second order, and so on, as I explained in the previous slide. Okay. See, low order streams have short lag time between the rainfall and the floods, okay, and are more prone to flooding. So, if you are having, like for example, dendritic pattern in the area, then you will have the likelihood of having very quick flooding event or the flooding in that particular area. Okay. And the higher order streams, okay, with many tributaries are less prone to flooding. Now, coming to the bifurcation ratios, as we were talking about, that if you have two lower order streams meeting at one point, then the next one flowing down will become the higher order stream, and so on. Okay. So, we are having two single order streams and then getting into the second order, and two second order getting into the third order. Okay. And the bifurcation ratios has been given in a very simple equation, Nu by Nu plus 1. Okay. So, where Nu is your number of segments of a given order, and then next one is the another higher order segments. Okay. So, based on that you can have the bifurcation ratio. For example, here Nu 10, okay, is for the first order you are having. So, you are having 10 stream, and then the second one is you are having 3, that is the next higher order. Okay. So, you have the bifurcation ratio between these two is around 3.33. Okay. So, this to some extent helps us in understanding that what type of the runoff we will expect or the hydrograph you will expect in that particular basin. Okay. So, this is given for the second order, that is the ratio between the first and the second one. Okay. Now, drainage morphometry, if you take, okay, so drainage network of river basin shape and channel pattern are most vital morphometric parameters factors that play significant role in increasing rate of flow through the drainage system, that is what we are talking about, the runoff. Okay. And it has been seen usually that if you are having higher bifurcation ratios, higher will be the discharge, and if you are having lower bifurcation ratios, you are having lesser discharge. Okay. However, for example, which has been shown here, okay, you are having one elongated shape of basin, another one is rounded shape. Okay. And the area is more or less similar, but if you look at the hydrograph of this one, they varies. Okay. So, what one can expect based on this, that this area will yield a very quick or maybe less discharge here. Okay. But what we found was that the elongated one, because the travel time which has been taken here will be different than this one. Okay. So, what has been seen here, that even the bifurcation ratio, so one is the shape, another is the bifurcation ratios which we consider here. So, if you have that what we have talked, higher RB values, higher will be the discharge, lower RB, lower will be the discharge. However, even with the higher RB values in the elongated basin, okay, so this basin had very high density and higher RB values. Okay. The hydrograph is very smooth, okay, suggesting less discharge. Okay. And the rounded one, which almost like having the same basin area with low bifurcation, because streams are not much. Okay. That means the runoff will be very low, but it shows very high discharge. Okay. The reason is that the smoother curve of the narrow basin, okay, this is this one, the elongated one with higher bifurcation ratios, which is around 10 for example, okay, can be explained by greater time lag. Okay. So, even this basin had a higher bifurcation ratio, the shape played an important role here. Okay. So, it took longer time to pour out the water at this point. Okay. Hence, the hydrograph which has been seen was quite smooth. Okay. Whereas, in the case of the rounded basin, which had the bifurcation ratio very less, hence we should have expected lesser discharge here, we got very high discharge here. Okay. And this was mainly due to that the time taken from the upper ridges, middle part and the lower ridges of the rounded basin, it was less time which was been taken, causing higher discharges in the region. Okay. Now, another important one is that based on the drainage basin area, you can talk about the drainage density. Okay. So, you have the drainage density which is given as D is the ratio between the total length of the stream. Okay. So, all streams you add in, the length of the streams in the basin and the drainage basin area, that will give you the total drainage density of that particular region in kilometer per kilometer square. Okay. And it has been seen that the measurement of the drainage density provides a hydrologist or a geomorphologist with a useful numerical measure of landscape, dissection and runoff potential, because the drainage density will tell you that what will be the runoff potential of that particular area. Okay. Of course, you will also be able to make out that what type of material is available, because that on, for example, on a highly permeable landscape with small potential will have small potential of runoff. Okay. In that area, the density Runott density are sometimes less than 1 kilometer per kilometer square. Okay. On the highly dissected surface, okay, runott density of over 500 kilometer per square kilometer are often reported. Okay. Closer investigation of the processes responsible for the runott density variations have discovered that number of factors collectively influence the stream density or runott density, and this factors includes climate, topography, infiltration, okay, vegetation and the geology. Okay. If the infiltration dominates over runoff, tends to have lower density in that particular area. Now, for example, here this basin, in this particular area the runott density is quite low, and the reason is because the area is comprised of sandy hills. Okay. So, you have very fast infiltration in this particular region, okay. Hence you will have lower runott density in that area. So, basin shape, even if you take, the hydrographs will vary from place to place. Okay. Even if when you keep the rainfall almost constant in for all the basins. Okay. So, you will have lower discharges here, very high here in this area, you will have higher here, lower here, and you will have lower, higher in this type of basins. Okay. So, shape of the basin and runott density helps us in identifying that which area will have peak flows or runoff and amount of runoff in that particular region. Okay. Channel pattern if you take, okay, or channel discharge you have to take, you need to have certain parameters like width of the channel, depth of the channel and the velocity of the water flowing through the channel meter per second. Okay. So, this is what you are having. Okay, fine. For example, you are having the cross sectional area is 25 square meter and you are having the discharge here, okay, is 5 meter per second, and then you are having the total discharge if you take will be around 125 cubic meter per second. Further, this is one sketch which I would like to discuss here is the runott texture. Okay. So, if you are having different type of rocks, okay, like you are having gabbro, again these are all the igneous rocks, granites, and then you are having sedimentary rocks like sandstone and shale. Okay. The runott textures will vary. Okay. Like for we can classify this as an coarse, medium or fine. Okay. So, coarser will be low runott density, develops on hard and resistant rocks. Okay. Like for example, here which will have coarser, we can classify this as an coarser runott density, okay, or runott texture. Medium is moderate density, develops on hard with moderately permeability, okay, or permeable rocks. Okay. Then you can have something like this. Okay. You are having medium, and if we are talking about the fine, then we are having where low permeability is there, where you are not allowing much of the water to percolate down. Okay. Then you will have the very fine runott texture. Okay. Now, this is one of the method which has been followed to talk about the recurrence interval of the floods. Okay. Like for example, here what has been given is the one is you are having the years, then maximum mean discharge, okay, and then you are having, based on that you have ranked those events and then you have calculated the recurrence here. Okay. So, for example, you are having the maximum discharge in this list is 1440, we can rank 1 and then 2 and then 3 and so on. Okay. Now, if you look at this is the data which is available from the Colorado and Thompson River, where you are having the number of So, it is almost like 25 years if I am not wrong, okay, for 25 years, and based on the discharges one can classify this. So, you are having maximum discharge which was experienced in 1965 and 1520 cubic feet per second, and then you are having second, third. So, these are so on, you can classify this, okay, based on the discharge. And if you want to find, for example, the recurrence here, so we have shown in the next slide for this, and if I am not wrong for this one, okay. So, in the next slide how we can see the recurrence, okay, for that, okay. So, if we look at finally this one, okay. So, how to calculate? Suppose the record of the maximum mean discharge by a particular stream each year have been kept for n years, okay. Each of this yearly maximum discharge can be given a rank m, okay, where rank 1 stands for the maximum in this years. A recurrence interval can be calculated as r equal to n plus 1 by m, okay. So, you are having, for example, where n is the number of years recorded. So, you are having the data of 25 years, for example, and then 25 years the maximum discharge was recorded during year 1965, okay. And that was along the Thompson River, okay. That is 1520, which ranks first. Therefore, if we would like to know the probability of such event, then what we can say, that we can have n plus 1, that is 25 plus 1 by 1, okay. So, every 26 years you will have this type of events, okay. Now, for example, another event like we are taking to like 1971, remember the previous slide, okay. So, discharge which was around 1030, okay, and that was been ranked as 7th, okay. So, then we can have 25 plus 1 by 7. So, the recurrence of similar event will be in a time gap of 3.7 years, okay. So, this is how we can talk about the recurrence interval of that particular event, provided the rainfalls remain same and provided the landscape does not change, okay, fine, but that is not possible, okay. But one can try, even one can think of having this information, okay. Now, flood controls, mainly what we do is that the river channels or channel is considered to be in flooding stage when runoff water spills over the banks, okay. During floods, stream carries and deposit excess sediment bed load, hence it required that the channel should be periodically cleaned, okay. And this is one of the reason in the Kosi region where we are having lot of sediments which are been poured in the downstream during monsoon, and we are having less and less cross sectional area, okay. So that the river bed level is not raised and the heights of the banks are deeper enough to provide easy way to the next flood water to pass through and through, okay. Additional flood protections can be gained by constructing shorter walls adjacent to the bank, what we are terming as the artificial levees, from 1 to 3 feet high, which may allow some vegetation to grow within the river channel, which in turns benefit the wildlife also, fish population and scenic view along the river, okay. Now, this is the hydrograph which shows that what happens if you keep on having construction close to the river banks, okay. So, this you are having the period of rainfall, you are having, okay, and this is the hydrograph, original hydrograph of the stream flow. But after the construction, what happens is that you are having very fast stream flow, okay. That is because of the urbanization, okay. So, this is the the original time lag between the two. Okay, fine. And this is the time lag after the urbanization. So, you are leading into, or urbanization, you are covering more area, not allowing the water to percolate down, okay, and you are putting more runoff. So, very quick discharge, very quick runoff will be experienced if you are having after the urbanization. So, this is an example for that, okay, which shows that the areas close to the banks were occupied by fill during the construction. So, you had the initial, that is the first, you can say this is the natural channel, and then you are having the height of 25-year flood in unmodified channel. Okay. So, this was during an unmodified channel. Now, after this area was been occupied, so buildings built in old 25 years floodplain. Okay. So, you have occupied this because you never experienced flood during last 25 years. So, you occupied this having safe place and all that, but the discharge have gone. So, new heights of the discharge here after 25 years. So, this will be the new one. Okay. And then we keep on crying that we have been affected by the flooding events. Okay. This is an example from the city in Gujarat, Ahmedabad. In no time we experienced the flooding on streets. Okay. So, there are ways to do that. Okay. So, flood hazard zones and management strategy, if you take into consideration, then flood hazard zone 1, which we consider as an active floodplain areas. Okay. We should prohibit development of business and residential complexes, maintain area in a natural state. Okay. In zone 2, alluvial fans and the plain areas. So, these are the areas where we will put as in zone 2, okay, and with the channels having depth less than 1 meter. Density of the construction should be relatively low in such areas. Dry streams should be maintained in a natural state, or the density of the natural vegetation should be increased to facilitate superior water drainage and infiltration in that particular region. Construction of houses should be at local level. Okay. That is at higher levels one can construct this thing, okay, to avoid the flooding due to such shallower streams. Okay. Then coming to the flood hazard zone 3, these are the areas which are dissected uplands and lowland slopes, drainage channels where both erosion and depositional processes are operative along gradient of generally less than 5%. Okay. Similar to flood hazard zone 1, you can apply those conditions. Roadways which traverse channels should be reinforced to withstand the erosion powers of a channelized stream flows. Okay. And then flood hazard zone 4, which includes the steep gradient drainages, consist of incised channels adjacent to the outcrops, okay, and mountain fronts characterized by the relatively coarser bed loads. Okay. This is what we were talking about, the proximal part of the alluvial fan regions, okay, or the cliffy region along the fronts. So, for example, restoration, this is a very well followed practice. Okay. So, this is before the restoration people have done. Okay. The erosional sites have been restored and put with the rock blocks which restrict the erosion further, and then later what you see is something like this. Okay. So, this photograph has been shown before and this is after that. Okay. So, you have channelized the flow. Then further, there is an example from if I am not wrong, this is from US, okay, which shows the city in the flooding condition in 1958, but in 1956 after the channel was been like the flow was channelized. Okay. So, what they have difference between this two, you can easily make out that you can do this to channelize. This is from Tokyo, that you are having the major streams flowing across the this major city, okay, where the channel is almost like the flow is channelized in this region. Okay. Further, this is from Ganga in close to Kanpur. This again you may keep facing the flooding in the low lying areas, and one of the example, this is from Gujarat along the Sabarmati river, where this areas again was experiencing the floods every year. Okay. So, this area has been channelized completely, and what you see during the construction, this is what they call the river front now, and the beautification has been done, and you can see the present day is something like this. Okay, fine. So, you have created some good facilities and the for the people, as well as you have channelized the flow. Okay. So, one can do this to avoid the areas getting into the flooding conditions. Okay. There are some examples which shows that what happens if you are having the breach in the dams, and this is and construction of artificial levees you are having, but at the same time if the levees are breached, you may have problems in the adjacent areas. Okay. So, these are the elevated portion, okay, close to the bank, and then further you are having the low lying areas. Okay. So, this is again an example which shows the channelization of the river, which you can see here and which you can see here. Okay, after the flow has been channelized. Okay. So, even one can generate GIS maps, okay, to find out that which areas are low lying areas, and then come up with the flood hazard maps. Okay. Now, coming bit quickly here, this is an example which has been given for the Mississippi River, which marks the inundation during the flooding events. Okay. So, this is the normal condition, and this is during the flood event which happened 1993. Okay. So, you can mark easily that which areas were been affected. Okay. So, another most common method to control floods are by construction of dams in the upstream hilly terrains and small barriers or the embankments in the plain regions. Okay. This also we discussed towards in the beginning, that if you are having the detail of inundation of a different season, one can easily come up with a very detailed inundation map or the flood hazard maps in this region. Okay. And this what I was talking about, that this was been occupied in 2008. Okay. So, this color if you take, this is this one which has been shown here. Okay. So, in 2008 this area was been affected in the flood events. Okay. So, I will stop here and we will continue in the next lecture.